Greetings. Welcome to the 9th lesson in a series of presentations on basics of power systems engineering. This lesson covers electrical circuit analysis. There are two principal methods of analyzing electrical circuits. Those are the loop method and the node method. The lesson you're about to view covers loop method of analysis. Lesson 10 explains the node method or nodal method. Consider the circuit on this slide. A typical circuit analysis problem specifies all of the elements of the circuit, such as all of the resistors and all of the voltage sources and current sources if they are part of the circuit as well, and asks for current in one or more of the branches, or asks for voltages between pairs of circuit nodes. Loop analysis method, which is also known as mesh analysis method at times, offers a powerful systematic technique that allows calculation of branch currents for every branch of the circuit. From those currents, all the required voltages can also be easily calculated. Implementation of this method starts with assigning a loop current to each of the visible loops or windows in the circuit. In this example, we have 3 windows or 3 loops. Each loop current has a direction that's either clockwise or counterclockwise and has an index variable name such as I1, I2, I3 in our example. The direction of the loop does not really matter in our analysis, but it will make the development of the solution clearer if we pick the same direction for all loops of the same circuit. I typically pick a clockwise direction, as you see here. I need to point out that loop currents are fictitious currents, as obviously the same current does not flow in all branches of the loop. But they serve as a clever technique to analyze circuits nonetheless. The difference in currents in branches will be taken care of in the process of this analysis. The next step is to write the KVL in each loop, which results in several simultaneous linear equations that can be solved to find the loop currents. From the loop current, branch currents are easily calculated. I will indicate the voltages of the voltage sources and the resistance of the resistors, and we'll go through the application of this method in an example starting on the next slide. There are 3 batteries with some internal resistances connected in parallel, and the 3O of the batteries is powering a resistive load of 80 ohms. We are asked to find the current in all the branches and voltages across each resistor in this circuit. Let's assign the loop currents to each loop. Here they are, the 3 loop currents I1, I2, and I3. I will write the KVL for each loop at this point. To be consistent, we need to follow a convention for the sign of voltage drops and voltage rises. It does not really make a difference as long as we stay consistent. I typically take a voltage drop to be positive, which means a voltage rise will take on a negative sign. Here is the KVL for the first loop. You can start anywhere on the loop and go around and return to that same point, but for this example, I'm starting at this corner and going clockwise. The first voltage I come across is a 50 volt voltage rise, which with my convention would be a negative 50. The next one is a voltage drop of 4 times I1, because I1 goes through this resistor. And because it's a voltage drop, I add it to the list, plus 4 times I1. The next one can be considered a drop if I take it as 2 times I1 minus I2, and that would be a drop of 2 times I1 minus I2 written here with a plus sign. And the last voltage is a voltage drop of 50 volts, so it will be added as plus 50, set equal to 0, and that completes the KVL for this first loop. KVL for the second loop, again, if I start here, I have a voltage rise going clockwise. I have a voltage rise of 50, so that's negative 50. I have a voltage drop of 2 times I2 minus I1, and so I'll add that term. The next voltage I come across is across this 2 ohm resistor. The current through this one is I2, so the voltage drop would be 2I2, and that's shown here with the plus sign. The voltage across the 1.5 ohm resistor is 1.5 times I2 minus I3. If I were to consider it as a voltage drop, I2 minus I3 times 1.5 is added, and there is a voltage drop of 50 volts, so that comes as a plus 50. And finally, the I2 is going through this bottom 2 ohm resistor, causing another voltage drop here of 2 times I2, and that's shown here. The sum is set equal to 0, and what we have left is the KVL for the third loop, which is shown here. Again, if I start here, there's a voltage rise of 50 due to this voltage source, a voltage drop of 1.5 times I3 minus I2 in this direction, plus minus. So that's added as 1.5 times I3 minus I2. And the last voltage is across 80 ohm resistor, and that equals 80 times I3, and that's also a voltage drop, and that's written here. Next thing I do is simply cancel out the opposite terms and collect the like terms and so on to clean up these 3 equations, and here is what we end up with in terms of 3 linear equations in 3 unknowns. You can use a calculator, especially on an exam, because all you're allowed is a calculator and you don't have access to computers. Make sure you have a calculator that does simultaneous linear equations for you, and you can easily find the solution using a calculator. Here I used the Excel sheet, and the way I did it was to form a matrix of the coefficients 6, -2, and 0, because the third term here is missing. -2, 7.5, and -1.5 for this second line of equation. And for the third one, 0, because the I1 term is missing, -1.5 and 81.5. That's the 3 by 3 matrix of coefficients. If I multiply that by the vector of unknown currents, I1, I2, I3, I have to set then the results to 0, 0, and 50, the quantities on this side. To solve this, I took the inverse of this matrix, which Excel performs quickly and easily, and multiplied that inverse matrix times this vector here to get the I1, I2, and I3. And the answers that I found are on the next page. Here are the I1, I2, and I3 in amps. From these 3 loop currents, we can find current through each resistor along with the direction of those currents. Current in 4 ohm resistor is simply 0.0 in this one is 0.0451 because all of I1 goes through it. Current in the 4 ohm resistor, current in this 2 ohm resistor is calculated as I2 minus I1, and let's look at the rest of it. Current through the other two resistors, the top and bottom, are simply I2, although they flow in opposite directions. And current in 1.5 ohm resistor is I3 minus I2 times 1.5, and in the upwards direction. Current through the 80 ohm resistor is simply I3, which is shown here. I have marked each branch with the current in amps in that branch as well as the direction of each. Now that we have the branch currents, we do not need the loop current indicators or markers, and I'll remove those to reduce the clutter in the diagram. One check on our work is to verify the KCL for the nodes. Let's look at this node. You see that two currents are coming into the node and one current is leaving that node. So adding these two currents, we should get the value for this current, and you can see that checks out. Also for this node, there are two currents coming into it, this one, and they should add up to the current that's leaving the node, and that also checks out. Now let's find the voltages across each resistor. Voltage across the 4 ohm resistor simply is 4 times the current through it, which comes to 0.1804 volts. Voltage across this 2 ohm resistor is 2 times the current here, and that's the answer there. Voltage across the top and bottom 2 ohm resistors is 2 times the current through each, and they come to 0.2704, although their polarity would be opposite each other. And calculation for the voltages of the 1.5 ohm and 80 ohm resistors are shown here. 1.5 times 0.4808 for this resistor, and 80 times 0.6106 or 6160 is the voltage drop across the 80 ohm resistor, which comes to 49.28. To check our calculation of these voltages, we can verify that KVL is not violated in any of the loops, of course within the rounding limits of the rounding errors. Let's look at the first loop. I'll go clockwise direction again. There's a rise of 50 volts and a drop of 50 volts, so they cancel each other out, so I won't consider those. But the other two are equal and opposite, so I have a rise of 0.1804 and a drop of 0.1804 adding up to 0, so it checks out in this loop. In the other loop, in the middle one, again the 50 volt rise and 50 volt drop will cancel each other out. So let's look at the remaining voltages. As I move around, starting here, I have a voltage drop, another voltage drop, and a third voltage drop, and I have a voltage rise on this one. So the 3 voltage drops have to add up to the voltage rise. And if you do the math, you can see that some of these 3 will match this voltage here. So the voltages actually check out. For this one, for the last one, I have, again going in this direction, I have a voltage rise of 50. So let me write this one out. So negative 50 for a voltage rise. And then I have a drop of 0.7212 plus 0.7212 is the voltage drop, and there is another voltage drop of across the 80 ohm resistor of 49.28. And if you add these two, they come to positive 50, cancels out the negative 50, and I get 0 as well. We have reached the end of lesson 9. My name is Fouad Alvandi. I'm the founder and instructor at the online educational group Own Your Destiny. If you enjoy watching my presentations, please click on the subscribe button and the notification button or bell. You can also visit my website at the link shown on this page, own-your-destiny.mylearnworlds.com. Thanks for watching this video, and I hope to see you in another one of my presentations.